So in this video we are going to continue about what we were going to do in the last one, and let us just see what we can do from this one. So let us do a few problems first, and then we can start up doing some of the basic theorems, which are like the chain rule and stuff like that, because those are really very and you need to be able to do them very quickly. So let us do this one. So observe, we need to show so we want to show that f from r squared to r defined by the function f of x comma y equals to square root of modulus of xy is not differentiable at 0 comma 0. Now, well, this is a different type of a problem here, and we are required to show that something is not differentiable rather than differentiable. So what we do here, well, of course some conditions are need to be found, like if you understand that f of x comma 0 is the same as f of 0 comma y, because all of is the same as f of 0 comma 0 and all of them are equal to 0, right? So this means that if we were to find a derivative, we can see the limit h tends to 0 by mod h, and this should be equals to limit h tends to 0, and since this is already 0, we can write it as 0. Similarly, if we just take the y coordinate, we can still see that this part is again 0. So these two limits turn to 0, and what is disturbing here is that obviously if the derivative were to exist, it has to be 0. But now what we see is that limit f of a plus h b plus k minus f of a comma b so let's say this is the limit we want to find, because if 0 is the unique derivative, then this must be the answer. But now we see that, so we are evaluating at the point 0 comma 0, so it's like f of h comma k, so it's root over modulus of hk. Actually it's root over a plus h into b plus k, so let me just write that down. So 0 plus h into 0 plus k, and minus f of 0 comma 0 is 0 and the derivative is 0, and therefore and the numerator, this one is just h comma k, right? This gives us limit h comma k tends to 0, and this is just root over of modulus of hk divided by root over of h square plus k square. And it is very well known that this limit does not exist, because what we can do here is we can see this limit does not exist, because we can see that for h equals to k we have the sequence limit h comma h to 0 mod h, because that's root over h square, divided by 2 mod h is just equals to 1 by 2, not equals to 0. So this limit is not unique, that means it does not exist, therefore it is not differentiable. Therefore the function f of x comma y equals to root over of mod f x y does not have a derivative at 0 comma 0. So this is what it basically means. Now this is obviously one of the ways we can find out the derivatives, but there are of course other ways we can show that this is not possible. But for instance, let us take a look at another problem. So this is the required function. Just take a good look at it first, and I'll give you like 10 to 15 seconds to think what to do with it. So we basically need to prove that this function is not differentiable at 0 comma 0. So try to find a way to prove that thing. So as you can see that obviously x mod y by root over x square plus y square, and you can see that the difference in the definitions are quite visible, but it still is some basically one of the same definitions that we have used in the above image, because if we were to really find out how to do this problem, then we need to go back to the basics, and we need to go back to the basics of iterated limits, where we learned how to prove that a limit does not exist. So we take different paths along the limits, we play around with the definition of the limit, right? So let us see. First we need to write down the corresponding derivative. So obviously if the derivative were to exist, we would guess that it is 0. This is because limit zero by mod h is equal to 0, and also limit k tends to 0 f of 0 comma k is mod divided by mod of k would also be 0. So this is why we would consider that. Right. If the derivative were to exist, it would have been 0 now. Divided by h comma k. Now this limit should be equal to 0, and that's what we are required to prove, and it should be 0 exactly. If it is not, or if it does not exist, then the derivative does not exist at 0 comma 0. Now and therefore it would seem that the function inside the limit simplifies to the following: h mod k divided by h square plus k squared. And we can see that the limit does not exist by a various methods, but the simplest one is that along the path we have h squared divided by 2h squared, which is basically 1 by 2, and it is not equal to 0. So we can conclude that the limit does not exist and the derivative does not exist, so it's not differentiable at 0 comma 0. So this would be how we would be approaching this problem. Now what we can do is we can do a ton more of problems later on, where we would be doing only problems, the solved problem sections later on. But for now, let us do some basic theorems as well, because they would be required. Now the most important of all is obviously the chain rule. Now we have studied the chain rule in our previous section in one variable calculus, where we were doing the chain rule. Now what we are going to do is we are going to study the chain rule for this multivariable case, which is of utmost importance. So basically, what does it say? So this is how the chain rule works. It's like the same as with the single variable case, but here it says that if f is a function from r to the power n to r to the power m, and it is differentiable at a, so notice that f of a belongs to r to the power m, and we have a function g which goes from r to the power m, so it takes in values from r to the power m and gives in values to r to the power p, and this function g is differentiable at f of a. Okay, because remember that it can be, because f of a is a entry from r to the power m and g has the domain of r to the power m, right? Then the composition g circle f, or g of f basically, which goes from r to the power n to r to the power p, is differentiable at a, and the differentiation is given by this. Well, this can also be written as this in simple terms: g prime of fa, as we used to write in the functions where we had the old chain rule, but this is just a same. Okay, now, well, this is the rule that we are going to follow, and there are other rules that we would also see, but first, some properties about chain rule is very important. In the multidimensional case, we need to understand them carefully. If f from r to the power n to r to the power m is a constant function, okay, is a constant function, that is, for some y belongs to r to the power m, we have f of x equals to y for all x belongs to r to the power n. So no matter the input, the output is always y for some y. That is how we called it a constant function. Then d of f at a equals to 0 for all a's. Okay, so the derivative is 0, and it is, as you can see, it's similar for all the functions. It's similar as an analogous to the one variable case. If f from r to the power n to r to the power m is a linear transformation, then d of f at a is basically f. Right? Okay. Number 3. This helps us do the derivatives very easily now, because what we see is this: if f is from r to the power n to r to the power m, so this is the condition that if has like m component functions, which it must have when it gives out a value to m, and this component functions which f had, if all of the fi's are basically differentiable, only and only then we have the whole function differentiable, and the answer is given by df1a, df2a. They can be individually sorted out, right? Now some of these things would require proof and some of them would not, because the first one seems like a pretty easy thing to do, because we can prove the first one as follows. Since f of x equals to y for all x belongs to r to the power n, and we need to prove the derivative is 0, so let us prove it at an arbitrary point h. Limit h tends to 0, f of a plus h minus f of a minus 0 divided by mod h. So this limit should be 0, and we see that limit h tends to 0. Now f of a plus h is y, so is f of a, because it's a constant function, right? And of course with the norms. So this is basically 0 because the numerator has norm 0. So therefore df of a is basically 0, right? Number 2, so since f is the linear transformation here and we want to prove that the derivative is itself, we can say the following limit f of a plus h minus f of a, and this answer should be f of a into h, right? So this should be the answer that we are looking for, and it shouldn't be f of a into h, it's basically f of h basically. So we can cut this part down, because when you have the function f and the derivative d of f h should be given by f of h. So because that is what we are trying to prove here. But since f is a linear transformation, we see that if you were not clear about this, so there exists a linear transformation lambda h, but we want to prove that the linear transformation is basically the linear transformation that we had before. So starting with the linear transformation, that linear transformation is always differentiable. We have proved that the linear transformation is always differentiable in one of the previous videos. So in this case the answer should be f of h, the derivative should be f of h itself, and we are trying to prove that this limit is 0 so as to establish that fact that the derivative is itself. So we see that since f is a linear transformation, it follows the property of a linear operator. So f of a plus h is basically f of a plus f of h, and we already had minus f of a minus f of h equals to 0 because the numerator is 0. Now this can again be done because we see that this kind of problems can be easily done using all the proper things. Now the proof of number 3 should be is something like this. Now we know that we can assume that each fi is differentiable at I. So if each fi at A, and we are claiming that the derivative is this, now what we want to prove is that limit is true. Now we can see that f of a plus h minus f of a minus lambda h is basically equal to, now this whole thing can be found out because it's basically a vector now and f as component function. So we can see that the first component is this minus this minus this, second one is this, and similarly the last one should be this, right? Now therefore limit h tends to 0, f of a plus h minus f of a minus lambda h divided by norm of h, this limit then should be equal to norm of, we know this vector is basically represented as this, and when we take the norm of that, it's basically a summation but in square root form. But we can, since we have already proved that that is less than equals to the mod of that, so what we can find is this is less than equals to summation I equals to 1 to m fi of a plus h minus fi of a minus dfi of a mod of this divided by mod of h. And we do understand that this, all of this limits goes to 0. This is because since fi's are differentiable at a, so because this is true, we know that limit h tends to 0 fi of a plus h minus fi of a minus dfi of a, which is basically the derivative for fi, divided by mod of h equals to 0 for all I belongs to 1 to m. And that is why this is also true, and this proves that the limit is 0, right? So this is another way of doing it. Now if we are given, let's suppose we can turn our attention to a more simplified problem. I hope we can do that. So let's say if and s of x comma y is basically x comma y, then we need to prove that ds of a comma b is basically s itself. It's basically s itself. Now how do we do that? Well, we see that we can directly find out the limit here. Limit h tends to 0, and let us see the norm, because it will be normally a modulus, because you understand that firstly because the output is always a real number, we can have a real number here. So what we have here is as follows. S of a plus h minus comma b plus k minus s of a comma b, and we are calling the linear operator lambda of h comma k, which is basically s itself. Now we want this limit to be 0, or we want to prove that this limit is 0. So let us see how we can do that. Well, s of a plus h comma b plus k is basically equal to, since s of x plus y is defined like that, so a plus b plus h plus k, this is like minus a minus b, and lambda of h comma k, since we want the derivative is itself, it's basically minus h minus k divided by root over of h squared plus k squared. But this is equal to 0 since the numerator is 0, and therefore it is proved that ds of a comma b is simply s. We can find out another one. We can find another one which is as follows. Given that p goes from r squared to r and is defined by p of xy equals to x dot product y, right? Then dp of a comma b x comma y, so derivative of p basically is equals to ay plus bx. So this is what we want to understand here. Thus p prime of a comma b is basically the reverse, which is b comma a, where x and y are basically the coordinates, right? It's basically b comma a. That's what we want to prove. Now we are given that p of x comma y is basically x circle y, so x dot y, right? And we want to prove that like this is true. So this is the linear transformation. So lambda from r squared to r should be is defined as lambda of x comma y bx plus ay. That's how we are going to define it as. And we want the following limit to be 0. So limit h comma k goes to 0 modulus of p of a plus h comma b plus k minus p of a comma b minus lambda of h comma k and this should be equal to 0, or we need to prove it. Now we understand the function and we can write it as limit h comma k goes to 0, and this p of a plus h comma b plus k, this becomes basically a plus h multiplied by b plus k minus p of a comma b is just a cross b. And now lambda of h comma k, this basically is the derivative that we are talking about, and this derivative should be equal to bh plus ak, right? Now limit h comma k to 0. Now if we were to do this, you would find the following: a dot k plus b dot h plus h dot k minus, now bh plus ak is simply is bh b dot h minus a dot k, right? And this is root over of h square plus k square. And now the things cut off, and what we are left with this limit h comma k goes to 0, and modulus of h dot k, which is like the dot product between h and k, that is equal to mod h mod k, and of course the angle between h and k, and this is root over of h square plus k squared, right? Well, this is how it works. And now h and k basically do not really have this, but we can write this as less than equals to limit h comma k goes to 0 mod of hk divided by root over of h square plus k square, right? Now this limit basically can be found out to be 0 because this, since mod of h is less than equals to root over of h square plus k square, and mod of k is less than equals to root over of h square plus k square. Therefore, now the actual limit was this, so I would rather write it as limit hk tends to 0. We need to write it once more. P of a plus h comma b plus k minus p of a comma b minus, you had lambda of h comma k divided by h comma k is norm less than equals to actually limit h comma k goes to 0, and what you have here is h square plus k square divided by root over of h square plus k square, but this is equals to limit h comma k goes to 0 root over of h square plus k square, which is undoubtedly 0, and it exists as well. So we find out that this limit is 0, and therefore we can conclude that therefore dp of a comma b for h comma k is lambda h comma k, which is bh plus ak, or in other words p dashed of ab is simply equal to b comma a. And that's how this works. So I hope this entire video was useful. So the embedded video with this would always obviously be that of the derivatives one, with where the chain rule examples and solved problems are there. So that's a pretty long one, but that would be there. So we'll see you in the next video. The derivative of a function f of x at x equals to a is given by f dashed of a equals to limit x tends to a f of x minus f of a whole divided by x minus a. So this is the definition of derivative of a function, and we can use it to our advantage to find the different derivatives. Now let us begin by solving different basic derivatives first, and then we can do the other ones later. So What are the derivatives that we're going to find? So trigonometrical identities are a great way to start off this list of chapters. So trigonometrical identities. Trigonometrical identities are a better way. So the derivatives which we are going to find is sin x and cos x. So let us begin by one of them. So sin x. Let f of x equals to sin x, then the derivative of f of x is, so now we try to find the derivative using first principles, and it won't be that much hard because as we have already encountered this kind of problems before, we shall be accustomed by now to as to how to approach this kind of problems and how to solve the particular limit. So here, as you can see, the question asks us for f of x equals to sin of x. So the limiting definition would be limit x tends to a f of x minus f of a by x minus a, right? Another definition for the limit is what I am going to write now, is the definition what we are going to use while solving the problems. This is limit h tends to 0 f of a plus h minus f of a divided by h. This is a more standard definition of derivatives, and I think this is more useful than the other one, because the first one is usually the one where we convert from limit to derivatives, but this one actually helps us to find the derivatives in terms of the functions, elementary functions, directly from the limit. So using the value of f of x, we can write this as like this, right? Now we can use the formula using the formula for compound angles, that is we can add and subtract angles inside sine, and we can also express them. So we can use the formula sine of a plus b equals to sin b cos a. So this is the formula, right? So using this formula, we can see that sin of a plus h similarly would be now. When this is done, what we can do now is we can find the limit L. Actually here we do not read the answer L, we already have a name for it. So f dash a is equals to limit h tends to 0 sin a cos h plus sin h cos a minus sin a divided by h, right? So what we can do is limit h tends to 0 sin h by h into cos a. So we can just take the second term here, and we can take the first term common, and we can write limit h tends to 0 1 minus cos of h by h, right? So this limit is 1, so it becomes cos of a, because we have learned about the limit extends to 0 sin x by x in the previous videos. And the next one, sin a into, now we first use the formula for 1 minus cos theta is equals to 2 sin square 2 by theta. So using that formula it becomes minus 2 sin square h by 2 by h, and this limit goes to 0, because firstly sin h by, if it was sin h by 2 we could have found the answer, but since it is sin square h by 2 it goes to 0, so the answer is cos of a. So the derivative of sin of x at the point a is cos of a, right? Okay, we can do a similar calculation for cos of x as follows. So case 2 is, now the derivative would be defined as follows. Defined as follows: f dash a would be equals to limit x tends to a f of x minus f of a by x minus a, from which we can substitute h equals to x minus a to find the new definition which was more useful to us, which is like f of a plus h minus f of a divided by h, right? Now this would give us limit h tends to 0 cosine of a plus h minus cosine of a whole divided by h, right? So this means now we have to use the formula. Now trigonometry that cos of a plus h is equals to cos a cos h minus sin a sin h. Using this formula what we can do is as follows. Using this we have f dash a equals to limit h tends to 0 cos of a cos of h minus sin of a sin of h minus cos of a divided by h. So we can again distribute it as follows. Take cos of a common and we can write it as limit h tends to 0 cosine of h minus 1 by h minus sin of a common limit h tends to 0 sin of h by h. As we know from the previous example, this limit is 0, so this is 0 minus sin of a into 1, because this limit is 1 as we have done in previous examples, so the answer becomes minus sin of a. Okay, so that's the derivative we were trying to follow. A third example now could include the derivative of e to the power x. Derivative of e to the power x. So let f of x equals to e to the power x. Then let us evaluate the derivative at the point x itself. So what we are going to do is we are going to write it like this: h tends to 0 f of x plus h minus f of x divided by h. Okay, so this tells us limit h tends to 0 e to the power x plus h, because f of x is e to the power x. So f of x plus h would be e to the power x plus h minus e to the power x whole divided by h. We using the rule for indices, the law of indices, we can write this as e to the power x into e to the power h minus e to the power x whole divided by h. Now we can take e to the power x common, as the limiting variable is h, so e to the power x is basically a constant here. We can write e to the power x into limit h tends to 0 e to the power h minus 1 divided by h. And as we know from previous experience, this limit is again equal to 1, as I have proved. So the answer is e to the power x. And as you can see, the derivative of e to the power x is e to the power x itself, which actually means that we can find the derivatives very clearly here, and this is the only function whose derivative is itself. Now once we are clear with the basic definitions of how to find derivatives, I can give you a list of basic functions and their derivatives. So let me write it down. List of common functions and their derivatives. So now I'm going to write down all the functions and their derivatives, and from the next video onwards we would be trying to implicate them and learn more about the chain rule. Okay, so the more we learn about the chain rule, the better. Okay, so derivative is usually written as d dx, where x is the derivative variable, and in bracket we write the function which we are differentiating. So this is the format that I am also going to use. So these are the three functions. Firstly, d dx of x to the power n is n into x to the power n minus 1. d dx of ln of x is 1 by x. d dx of a to the power x is a to the power x into log of a. Number 4. Is a to the power x. Number 5. Number 6. Of tan x is basically equals to sec square x. Number 8. d dx of cot x would be equal to minus cosec square x. So I think these are some of the basic things, and there are other things as well that you need to know, but for the time being this should do. This should actually work pretty well. So let me write down some more rules. If fx and gx are two differentiable functions, then d dx of fx plus gx is equals to d dx of fx plus d dx of gx. So basically, if you are given to find out the derivative of the sum of two functions where both of the functions are differentiable, then the answer is basically the derivative of the first function added with the derivative of the second function. Similarly, if you are given something like this, where you have given the multiplication of two functions, then what you can do is try this. And finally, if you are given two functions in the form of division like this, then the answer is simply gx whole squared gx into f dashed x minus fx into g dashed x. And obviously here g of x not equals to 0. So these are the three rules also that you need to follow when solving for derivatives. And along with this, the most important theorem of all is the chain rule, which we shall do in the next lecture, where we after that we can be free to evaluate any derivative we want by hand. It's a magical rule, so evaluating derivatives won't be a problem anymore once you learn and once you get a hang of that rule. But before that, you need to be very much confident about all these formulas. You need to memorize them by heart so that you can just tell them at your lips. Let us begin with the chain rule. The chain rule states that the derivative of a composite function where f of x is continuous for all x belongs to u, where g is a function such that it goes from d to u, and g is continuous and differentiable at x belongs to d, then the derivative of the function f of g of x is given by f dash of gx multiplied by the derivative of gx. So it might look that it's not such a big result, and okay, the definition might be a bit more complex, but the result itself says that the ddx of f of gx, considering all the other technicalities solved, that f is continuous at g of x and f is differentiable at g of x and g is differentiable, we can say that the function f of gx can be differentiated by just differentiating the function f at the point g of x and then just differentiating g of x at the point x and multiplying them together, right? But this simple definition is the key to solving all of derivatives problems, as you can see now. So if you remember the basic derivatives, which I can recall one by one, it's like x to the power n is n into x to the power n minus 1, sin x is cos x is minus sin x and stuff. Then logarithm of x is 1 by x, e to the power x is e to the power x itself. Now we can try and find out the derivative of. So we are going to do a bunch of problems now. So let us do ddx of e to the power ax. So ddx of e to the power ax. So first recall the basic function. The function, what it starts with? It starts with the function e, right? E to the power something. Now what is the most basic representation? It's e to the power x. So if you remember, ddx of e to the power x was e to the power x, right? So we are going to copy this and write the answer itself. That is, the answer should be whatever is given. So e to the power ax, right? So pretend as if this function was e to the power x only, and write the whole function down. But then multiply it with, go to the next level of the function where the anomaly is present. So it should have been e to the power x, but it isn't, right? What is there instead of x? It's a of x. So now it should be ddx of ax, where a is just a constant, and when you do a constant x, a times x, the ddx of x is just 1 and constant just comes out. So the answer becomes a into e to the power ax. This is because ddx of x is just 1, and also ddx of a constant c times any function f of x is just c times the derivative of the function. So the constant just remains multiplied throughout. Okay, next example. Because the more examples we do, the more it would be easier for you to understand. ddx of ln of, let's say, x squared. So how do we do this? Well, first we try to think what the ddx of ln of x is, because the first function is ln of x, right? So ddx of ln of x is equals to 1 by x, right? So pretend as if this function is ln of x, and we write the derivative as 1 by x square. So do not directly write 1 by x, because you just need to pretend. But when you are going to write the derivative, you are going to write the same thing, and instead of x, whatever is present, you are going to use that. But you are just pretending it is x, right? Now you multiply and you do the derivative of the next level, the expression which is present instead of x. So x square is present here, so we do x square. So it is 1 by x square into ddx of x square by the rule for differentiation of powers is 2 into x to the power 2 minus 1, right? So it will become 1 by x square into 2x, which will give you 2 by x, right? Okay, one more. Let us try to evaluate ddx of log of sin x. Now, how many layers are there? Let me just clarify this like this. Layer 1 is the first layer of function. This is log. So layer 1 is log x. And what is layer 2? Layer 2 is sin x, correct? So it is log x and it is sin x. Now, the answer can be written directly if we have that in mind, because we differentiate one by one, and we keep on doing that until we reach the inner bottom where x is present. So ddx of log of sin x is simply equal to, firstly we do the ddx of log x, which is 1 by sin x, and then we do the differentiation of sin x, which is cos x, right? And cos x by sin x is simply cot x. So you see, we have got the answer. ddx of log sin x is just cot x. Okay, so this is not really a very hard one to be done. Let us move to other examples. We need to find the derivative of this function. So here comes the harder ones, or rather you can say the more complex ones, because if you know what to do, I do not think this would be at all hard for you any more than it for the last problem was. But then again, this would be a bit more calculative, right? So we first need to understand the layers and stuff. So what is layer number 1? Layer number 1 is of course sine of x, right? Sine and some x inside it, which we are going to pretend is x. Layer 2 is of the form fx by gx, right? Layer 2 of the is of the form fx by gx. which we learned before, that the derivative of two functions can be evaluated. How? I'll just write it down here, that ddx of fx by g of x can be evaluated as fx into g prime x, right? What is layer number 3? So in fx there are two layers, right? In fx there are two layers. How many layers are there? Fx has a layer which says that the inside function is x square plus 2. Similarly, gx has a layer which says that the inside function is e to the power 5x plus e to the power x, right? But these layers do not really matter because we already have a fx by gx thing here, right? So we are going to use them here directly. So let's do this. Let us first define the function as capital F of x equals to sine of, let me just copy it, log of x square plus 2 divided by e to the power 5x plus e to the power x, e to the power 5x plus e to the power x. Then f dash x would be, so firstly the derivative of sin x is cos x, so we first have this right, multiplied by, now we have the part where we do actually fx by gx thing. So this is gx, this is fx, so this should be squared. Squared means multiplying by 2 in the power, which is e to the power 10x plus 2 e to the power x. Then we have e to the power 5x plus e to the power x into the differentiation of log of x square plus 2. So first we pretend it's a log of x, so we do a by x square plus 2, and then we do the inside, which is x square plus 2, differentiating which you get 2x because the differentiation of a constant is 0. And if you remember, addition of two functions when differentiated is basically equal to derivative of the first function plus derivative of the second function. So here derivative of the constant is 0 and derivative of constant of x square is 2x, so 2x minus ln of x square plus 2 plus remains like that. And now we do the exponential. So firstly the exponential remains the same, so it's e to the power 5x plus e to the power x multiplied by, we do the 5x plus e to the power x, which is 5 plus e to the power x, so 5 plus e to the power x. So we can write it clearly here, cos of ln of x square plus 2 by e to the power 5x plus e to the power x multiplied by, now we can do a simplification here, x square plus 2 into e to the power 10x plus 2 e to the power x, and we can write it as follows: e to the power 5x plus e to the power x taken common, we have 2x minus x square plus 2 into ln of x square plus 2 into 5 plus e to the power x, and we can cut off this 5x plus e to the power x and this to give you the final answer, which is cos of ln of x square plus 2 divided by e to the power 5x plus e to the power x into 2x minus x square plus 2 into 5 plus e to the power x into ln of x square plus 2 whole divided by e to the power 5x plus e to the power x into x square plus 2. So this is our final answer, and obviously some multiplication in between. So this is the final answer for the problem. Thank you for watching. So please download the Breatter Maths app, which is given in the description. It is a mathematical app where you can find all the necessary statistical calculators like chi-square calculator, one variable means, population means, t-value, and much more. You can also find calculus related calculators like integration, derivatives. There is a section where you can find what's coming up next. There is a section completely devoted on mathematical notes where you can find notes on probability, statistics, calculus, and many more are there to come. In those notes we have already explained all the examples, all the problems and theory, and we are just covering the video lessons and solutions of those here. You can check that out. Also you can see the video solutions in a separate section where you can understand and give a feedback on what to expect next. You can ask for a problem, you can ask for a theory section as well. So please do check it out, and also do subscribe to Breatter Maths app and also its YouTube channel.